Hey guys, this is Sig, and I'm back with another Golang tutorial today. I'm sorry I've been away for a couple of weeks. I was traveling around. I was having a good time with my family over Easter. Hope you all had it to Easter, and it's time to get back into some Golang videos. Today we're going to be looking at pointers in Go. So pointers are, and if you don't know, references to places in memory that programming languages can use. Famously used in languages like C and C++, people get very scared about pointers, and pointers in Go can be a bit scary too. But we'll look a little bit about how they can be used, how you should be using them because it's a little bit different from C and C++. And let's dive right in. So here we are in our trusty neovite, one of them. And the first thing we're going to do is just look at what a pointer actually is in terms of syntax in Golang. So how do you declare a pointer? So a pointer is just another variable type, one other type. And you can actually declare, let's say my pointer, you can declare pointer by saying star and then the type that the pointer points to. So if you want to point to an integer, for example, you can say my pointer is star int, right? So now you're saying there's a variable called my pointer, which is a pointer that points to a value that is an integer. So what Go will then infer from this is that anything you assign to my pointer needs to be the address of an integer value. So what that means, for example, is that we can't say my pointer is equal to 2. This doesn't work, right? And the reason is, comes up in complaints, and the reason is that my pointer is not a direct int primitive type. We can't just say my pointer equals 2, because that would be just assigning it a null integer. Instead, like I said, a pointer always needs to be an address to something, basically something that the compiler can follow to find the actual type that you're saying that the pointer is pointing to. So in the case of our my pointer int, it needs to be an address of an integer. So how do we do that? Well, first we declare an integer. So we might say I is equal to 2, right? And then you might think you can just say my pointer equals I, but that doesn't work. That would be the same as what we just had. So instead what we do is we say my pointer equals ampersand I. So the ampersand syntax operator is what's saying you need to follow the address of this thing that I'm telling you. So in this case, we're saying follow the address of I, and then you'll get a pointer to int. And now you're saying, you can see it's actually happy. So if we print this out, we can say, what does my pointer actually look like? You might be a bit surprised by this. So if you run this little program here, you say that it says, by running for the tutorials, I'm going to print us this weird address. And this address actually changes every time we run it. We won't go into too much detail as to why it does that, but the TLDR version is that when you create variables in a program like this, it actually uses what's called the stack in your operating system, which changes or gets cleared every time your program executes and completes. So this is why we're getting a different address every time. So what if we wanted to actually get the value on my pointer? So rather than printing the address, which is kind of meaningless to us, maybe we want to print the value. The way we do that is we use the star operator again, and we dereference the pointers. This is called dereferencing the pointer. And what this does is basically say, not just follow the pointer, but actually give me the value that the pointer points to. So not the address like we just printed out, but the actual value. And you see if you run this again, it's now printing out 2 because the value I is 2 and my pointer points to that value. Because this is really, in a nutshell, how pointers work and how they work in Golang. And this is a concept that we can use in our Golang programs all the time. However, I will say, in Golang, it's a little bit different from C and C++ because the Go compiler actually does a lot of things under the hood. That means that you rarely have to do things like this. Like you'd rarely have a pointer to an int, unless you're writing something where memory is so critical that you really want to control everything. But the compiler does. You rarely want to use pointers to primitive types. And even when you're passing things into functions, if it's a primitive type, you're actually better off not using pointers. I think the Golang, sort of idiomatic Golang approach is not to use pointers in most cases because they are a bit more complicated, right? They're a little bit more, you're more likely to make a little mistake if you're using pointers than if you just used ints or primitive types right off the bat, right? So you need to be a little bit careful when you use pointers in Go. However, there are totally valid scenarios for using pointers. And really where they become powerful is when you use them in conjunction with structs in Golang. So let's treat a struct, for example. Let's say we have a struct. It's going to represent a library. So the library might have a name, right? It might have an address where the library is. And then it might have some books that the library knows about. So let's actually say that it has some books. And let's say they're of type book. We'll do a slice of book. So we need to define books. Let's go ahead and do that. So we'll do another struct, and that book is just something that has a title. That's all our books had. Now, this is totally valid Golang, and because book is such a simple struct, this is probably how you do it. But just for sake of this tutorial, we could also do this, right? We could also say books is actually a slice of pointers to book. So we're telling the Go compiler, you could actually follow the pointers inside the slice, and each of them will point to a book or be known, right? So this is something to be aware of. Pointers can be known. So let's look at how we could actually use pointers. So one of the really, really common use cases is, what do we want to create a library? We want to create a library that's efficient in our memory. So one way of doing that is by creating a so-called constructor method. So let's say we'll create a function called new library, and we'll say we'll pass in the name and the address. And then what we return is, again, the star operator for a pointer. We're going to return a pointer to a library or an error if something failed, right? So we're now saying when you call a new library, if everything goes right, we will return to you a pointer to a library. We won't copy over the whole struct. We won't trade a new, we will trade a new struct, but we won't copy over a new struct for you from something we've traded. We'll give you a pointer to the struct of this function created, just the one. So let's do some really simple validation here. Just to have an error case, right? So we're saying if any of these are blank, then we return nil, which again is a valid pointer. A pointer can be nil. So this is another use case for pointers. Is sometimes it's good to be able to say, something that's wrong. We didn't even try to create a library. We didn't incur a bunch of operational costs or memory costs. We didn't even create a library. It's just nil. There's nothing there. So we just say in that it's name or address. So it really matter. And then down here, we actually create a library. And now, what you remember that ampersand operator that we used before? Because we're returning a pointer to a library, we need to return the address of a library. So in this case, the ampersand operator comes in handy because we go in and we say we're now returning an address to a library for an address to a pointer to a library. And we'll just fill in our fields here. I will zip those. And then let's be good citizens and actually instantiate this slice. So we're saying alongside the things you passed in, we'll give you an empty slice for pointers. And then we need to return an empty error as well. Right. So this is a totally valid and the popular way of using construction functions in Go to actually create or to control how you create certain structs. Because we could have totally, since this is a public struct load, we could have totally just created, said my library equals ampersand library. We could have done this manually, right? Or we could have, not even ampersand, we could have just created a library instantiation like this, right? But the thing is, this way we control some of the logic around the construction of it, and we control the fact that it's always going to be a pointer. So we can actually go ahead and use this function now. So let's create a new library. So we'll say new library, and we'll say test lib, and the address is dummy street 123. And then we need to catch the error as well, right? So we're saying if error equals no, this is a common thing Golang, right? Whereas it doesn't equal no, we'll print out that something went wrong. But if not, we should be good and we can print out our library. Let's do that. So let's run this and see what happens. So this is an interesting thing. When you've got pointers to structs, you can see it behaves a little bit differently than when we had a pointer to a primitive type. When we had the primitive type, it just printed out the address, but the struct, it sort of knows, but this is actually what you're interested in is the struct underneath, right? And so you could, if you wanted to, you could print out, again, the address, right? But in this case, most of the time what you're interested in is you want to treat this as if it's not a pointer, as if you've just got the struct, and this is a powerful concept in Golang that you should definitely use, is the fact that structs behave this way. And now finally, let's create another function called add book to lib. And we'll be really explicit here. And we'll say you pass it a pointer to a library. And you pass it a pointer to a book. And then it tries to add the book to the library. So let's try this out. So we'll say, first of all, we should check if library is null, right? Actually, if library is null, old book is null. Because again, when dealing with pointers, you can actually run into the case where either is no. So let's say if either of these is no, we'll return a new error. Either this is not a great error message, but you hit the point, either pointer was no. If not, then we'll say follow the pointer to library and give me the books, and then we'll say append the books with the book, right? And then we return no. So now we have a function that can take a pointer to a library and a pointer to a book and add the reference to the book to the library. So let's try this out. So first we need to create a book, right? So we'll say in my book, and this is a book, like so. And we'll give it a title of my awesome book. Right. So now again, we have because I use the ampersand, we have a reference to a book. So now we can call add book to library, and we can pass it my library, and we can pass it my book. And now if we print that library again, let's see what happens. And then let's give you the best one here. So now we've actually got test live dummy streets, and we've got a slice full of, or with an address in there. So this is an address to a book, right? So this is really how pointers work. And what's the key thing here is that this could be anything, right? I've just traded these structs, but they could really be anything. They could be really big collections of things. This is generally when you use pointers, right? In this scenario, let's be honest, book is just a struct with a string. You don't really want to use pointers in this scenario. This is kind of bad practice, right? So what you would do is you would actually go out and say, just make a copy of it, right? So here we could there's a couple of ways we could do this, right? This would fix it, right? We could just say, don't worry about the fact that book is a pointer. Just copy the book over and put it into the slice. And the Go compiler would actually do a lot of things under the hood to make this pretty efficient. So this would probably be a more real life scenario, but we were explicitly using pointers to make a point. But the thing is, with this kind of pattern that you can use all over, you can actually really control how the memory in your program behaves and how you can use pointers to, for example, let's say library was a huge library with hundreds of thousands of book references in there. You don't really want to copy those around when you pass the library around. If you want to write a function, for example, let's say that the library function was like so, right? It could be that the Go compiler, when you called with a library like this, would actually copy the whole library over. Now again, the Go compiler is pretty clever. It does things, especially with slices, that would make it stop it from being a huge deal. But the concept is there, right? If library was called like this, there is a risk that it would be called by what's called by value, which would copy the whole contents in your memory, which would make your program take so much more memory than it needs to. Whereas this clever pointer approach actually is very easy to use, and it allows you to be explicit in how these things should be passed around and how you should manage your memory. So I hope that was a little introduction for pointers in Go for you, and I hope you enjoyed the video, and I'll be back soon with more. Thank you so much. Bye-bye.